Okay, counting down 5 seconds. All right, 2 minutes past. So, okay, let me start. First, welcome everyone. This is the room called Unify, and happen to be like today our talk is about unified processing with the Samza high-level API. So, what does this unify mean? Our theme for this unify is we want to be able to unify the batch versus stream data source in the Samza application. And also we want to be able to unify the managed versus the embedded mode of deployment mode. Also, the third unification theme is we want to be able to allow users to unify the single stage job versus multi-stage pipelines in a single Samza application in the new coming Samza release. So here's the agenda. Before I dive into this agenda, first of all, I want you to just take one big pause and then ask, recall the answers we got when we asked people why not using Samza. So there are a few pain points we heard. One, Samza's API is low, really low level, like a processing at the task level, which is really just a one shard of partition, and you're operating on one stage of the transformation. So if you want to write a multi-stage of pipelines, you need to write multiple tasks in the disjoint manner, and then you stitch them together with the Kafka topics in between. So it's not really easy and user-friendly for people who want to build a complex pipeline. That's one thing we heard. Second, okay, another thing that people say, no, I don't want to use Samza is because, okay, Samza deployment model, if you want to have a large parallel clusters, then you need to run Yarn. A lot of people saying, I don't know Yarn. I don't know how to run a Yarn cluster. So that's another thing. And there are also a set of people saying, I'm on AWS. And there, how do you run Samza jobs on AWS? The answer for the previous one is, good luck. You have to you have to like do the manual magic of doing a lot of like single process jobs and then manually sharding the partitions to the single process jobs in AWS, which is a big hurdle. Also, there are people who want to say, okay, want to serve some stream processing result directly from their processors. Say I have a web server, a web front server. I'm consuming some stats data from the Kafka topics, and then I get some aggregate results or some stats. I want to serve some RESTful calls, saying, okay, some people want to query this analytical data. I don't want to set up another set of a database to serve that. I want to directly serve from my Samza jobs, and no, you cannot serve it because Yarn dynamically identify the host that is running a Samza job, and where's your web server? It's hopping around in this cluster, so it's hard to set this up. That's the third, second one, and the last pain point we've heard is, well, not being the pain point right now, but it's more and more like a request coming from internally in LinkedIn. A lot of our offline users wants to move their business logic, the analytical jobs from the offline to the online. So their job is running on top of Hadoop and processing the HDFS files. How do you move on top of Kafka and processing the real-time job? So these are all the different asks and the pain points that user will say no to Samza before. And we pondered on the long time, and then this is our answer to that. We come up with a high-level API which allows user to specify and program multiple stages of a complex processing pipeline in a single application. We also, in this release, we also like allows the flexible deployment model. So users' Samza job is no longer only deployable to the young cluster. You can have your various different deployment models, different cluster management system, or your own embedded. You can embed the Samza processor into your own user application. Lastly, this new version also allows a very simple convergence between the batch and the stream processing, switching between the data sources from the HDFS versus Kafka without code change. We'll show all those in the agenda today. So first, we'll take a look at this very common application example. So this application is, the logic is very simple. You take the page view event as a Kafka topic, which is keyed and partitioned by the page key. And what we want to do is we want to count the page view events for each member in a 5-minute window, and then send the counter to the output, which is a Kafka topic page view event per member stream. So this is a pipeline that we see this often happen in LinkedIn, that people will first do a repartition of the incoming topic by the member ID. And then in the second stage, you use the window to aggregate the page views happening per member ID and emit the windowed aggregated counter. Now now the user needs to do a transformation to transform the internal representation of the counter to the output format, and then send it to the output Kafka topic, which is a page view event per member stream in this diagram. Now, how do we do it in the low level? So this is illustrating the application running in the using the low-level API. So these all visible in front of the user's eyes. User has to define a job 1, which is the page view repartition task, and create the intermediate topic, which is a page view event by member ID, deploy that, and then there's a second job, which is a page view by member ID counter task, which is doing the counter, window-based counter. And then this task will finally output to the final output topics. So this is the low-level API that showing the pipeline there. And user often need to create these intermediate topics and deploy different jobs separately. It's a lot of work, and we actually in LinkedIn we create a lot of tooling around that for users to be able to do this. So further, let's look at the code. So application in the low-level API has to write 2 different distinct code for that, program for that. One is this repartition job. So user code often like implements a stream task, and this repartition job is pretty simple. The process is just doing taking the input and then sending it to the output topic partitioned by the member ID. Second job is more the analytical algorithm. The meat is there. The basic logic is you need to create a buffer the incoming messages, and for each of the incoming messages, find the window partial result, counter result, increment that, and then periodically in the window task every 5 minutes, you need to calculate and emit the counters per each of the window result. So in Samza's low level, you need to implement 3 different APIs for that. The enable task to initialize the internal state store to hold those partial counters. B, the stream task, which is a per event processing API. So you need basically that's the interface that you process each message and increment a counter. Last one is the window task, which the method interface method is a window which is periodically emitting all those window counter results. In addition to do that, you can see that in the window and in the process, users also need to customize some code to do the counter and also to emit the result. That's another level of detailed implementation of how you get the partial counters from the Windows Store and increment that, and also periodically scan through using a range scan and emit the result. So it's pretty detailed and a lot of boilerplate for you to finish this simple counter job. And we say, okay, how do we alleviate the pains for the user who's writing just this pipeline? And this is what we come up with. In Samza 013, which is a coming release, we introduced a high-level API, which gives the user ability to express this multi-stage processing pipeline in a single user program. Now you don't need to separate them into two different tasks, the one doing the part of the job, part of the reputation job, and one doing the counter job. And then also looking at all this customized code to create a window partial counter, window store for the partial counter, and then do the incrementing of the counter, the emission of the window result. We provide built-in libraries to provide the high-level stream transformation functions, so you don't need to do this boilerplate implementing by yourself. So now, how the code look like? This is how it look like. Now, user only need to implement a application called repartition and counter example. In here, users specify the initial input and the final output of the streams, and in the program, user just say, okay, A, stage 1 partition by member ID, B, window, based on this window, the key tumbling window, using the member ID as a key, duration of 5 minutes, initial value is 0, and then I'm doing the counter increment. Then the map is a transformation of the window counter results to an output format, and send to is an IO operator that's sent to the final output stream. Those operations that is red circled are all building transform functions provided by Samza. So user never need to write all those boilerplate again. Oh, so another good question that we actually got from some external community users saying, hey, now you're helping me to do this partition by, and the system is automatically creating the intermediate topics for me. Then how do I know what is the topic name, and what if the next stage that is consuming from this topic is having a problem, and then there's a backlog there. How do I monitor my job? So in order, basically, in order to answer that question, you need to be able to visualize and know what are the actual input, intermediate topic names, and also the process names along this pipeline. So this is why we created a visualize the execution plan to illustrate this program. So I want to show you the better picture through the HTML file. So this is a bigger picture that I included in the slides. So here you see the original input is the page view event in blue, and then there's a partition by operator followed by the green oval circle. That's the intermediate topic that is automatically created by the system. So you know, by this visualizing plan, then you know, okay, this is the topic I'm going to monitor. This is the topic that belongs to my job. And then the following downstream operators window map and send to is here. Final output of the page view event per member ID is there, right? Okay, So let's get back to the slides. So now, just to recap, what are the operations we support as a building transform functions in the high-level API? This is a list. We have implemented a future map, flat map, and a merge, which are all the stateless operations. We also implemented partition by, send to, and sync. Those operators are all the I/O operators. You either send to or read back from a certain output streams or an external system. And then last two operators, window and joins, are all stateful operations. So in the first version coming out in 013, the states are all in memory. We're going to improve later to put the persistent storage for that. And based on that, also there are more features like event time processing and then the failure recovery that we can hook up with this. All right, so here, up to here, we talk about our solution for the first pain point, which is, okay, their programming API is too low level and it requires a lot of boilerplate for me to create this multiple state. Now, next, we will talk about how we provide a solution for the second part, which is I want to run my Samza job not in a Yarn cluster. So how do we solve that? We call it as like a flexible deployment model. First, let's look at what are the limitations with the current Samza deployment. Why is it so bad? This is the list of things we just summarize. So Yarn, well, so far Samza deployment has a tight dependency on Yarn. A lot of people saying, no, I cannot set up Yarn. I never had an experience. So just to run a simple Samza application, I need to set up Yarn. That's too much of overhead for me. And there are, as I talked about earlier, some other people, a lot of users are using Mesos, Kubernetes, AWS. So how do I run my Samza job on top of that? There was no answer to that before. And then last one is that the example I gave earlier. If I just want to run my Samza job on 3 boxes, and each of the boxes is serving some web requests, then I don't really want to have the heavy loaded way of setting up the cluster and then send my application there. So how do I do that? So those are all the questions and limitations that we heard earlier. Our answer to that is the flexible deployment model of Samza applications. We categorize as 2 different things. One is the Samza as a library, which come up as a new thing that allows the user to run the embedded stream processing in a user program. So you don't necessarily need a specialized manager Samza process to run your logic. You just instantiate the Samza stream processor inside your own program, and now you have the stream processing capability. There are also, then the question comes, okay, if I run Samza as a library, can I still do parallelism? Can I still have multiple different, many different processes working on the same set of data set? The answer is yes. So we have built in a Zookeeper-based coordination model between the multiple instances of a user program with the embedded model. So you can still have these coordination and partition assignments across all the multiple instances of the embedded process. So that's the first model, which is the Samza as an embedded model of Samza as a library. We still support Samza in a cluster. In addition, basically, the improvement here is, although it is still a Samza in a cluster, is no longer to be necessary a Yarn cluster, or more accurately, we prepare it to be pluggable. So you can, you run the stream processing as a managed program in a cluster. B, you can use a cluster manager to provide the deployment, coordination, and resource management. That's the feature that available in the Samza in a cluster. The new thing in 013 is the module that talk to the different cluster management system, it becomes the pluggable. So we can implement a different pluggable management system to talk to Yarn, talk to Mesos, and talk to others. So that's the quick overview about this flexible deployment model. Let's dive deeper onto the new one, which is the Samza as a library embedded model. These allow the full control of the user's full control on the application's lifecycle, the physical resource allocation, and the configuration and initialization. Thinking about this as a bare metal solution. So in this model, user find your own machine. You kick off your own process. But each of them will have a Samza stream processor embedded in your own process. Then, if you want more parallelism, just find more machines, kick off more process, and you get the parallelism. The coordination among the processes is not depending on Yarn. You can plug in a Zookeeper to coordinate between all those processes. So the picture illustrates this model. In this model, then Samza job is composed of a collection of standalone processes. It's repeated. You can see it's repeated multiple times as a stream processor in each of the in each of the user JVM process, and then one of them is going to be the leader, and all the others will be the follower. The coordination between all those processes are pluggable. The first implementation we have is this Zookeeper-based job coordination. It is used for the stateful use case. Because if it is stateless, you don't want to control which one is handling which partition, then you can just having a random assignment model. So you don't really. One of the example that in LinkedIn we had is we have a no-op coordination model, right? So, but for the stateful cases, if you want to have a stickiness of certain partition processed by certain hosts, then you need this Zookeeper, which has a more richer semantics in terms of, okay, what is the job model that job partition assignment do you have before, and you can stick to that. So in this model, then the job coordinator uses Zookeeper for leader election, and then the leader will do the partition assignments among all the active stream processes. Now, with this is a high-level view of how the embedded model will work in the single machine and among multiple machines. How the application code look like. The application code for the embedded model is very simple. This is a simple main method that the user will implement for this Zookeeper local application. User instantiated local application runner, and the Wikipedia application is a stream application that we showed earlier that does the pipeline processing. And the next two lines, all you needed. So the local, you use the local runner to run the application, and you wait for the finish. That's all you need to spin up this embedded mode of a Samza application. To use the Zookeeper coordination, these are two additional configurations you needed when you start this application. You need to indicate that the job coordinator factory is a Zookeeper job coordinator factory, and then the Zookeeper server connection string is the second configuration parameter. Now let's look at how the local embedded application launch sequence is. Following the previous example, then all you need to do is just to run my app.main. It instantiate the stream application, calls the runner.run this app. The local application will kick off the stream processors embedded in the program. So does this still work for the cluster environment? Next, that's what we show. So in the cluster environment, we're using the run app.shell script to kick off a remote application runner with the configuration of application classes my app.mystream app. Then the application runner will generate the execution plan for different if there's multiple jobs, then it will generate the execution plan to cut this into multiple jobs. And then for each job, it invokes the job runner to submit the job to the RM. In this case, just for the example, I show the Yarn execution. So the Yarn jobs are submitted to Yarn RM, and then it will kick off a job coordinator, which is in the app master process, and the app master will again invoke the run local app.shell script. This is exactly the same sequence as the embedded mode when you're running a single process on a local machine. So the only additional piece is where you submit and how you coordinate through the cluster environment. Okay, so finally, how will you make that happen? The key thing is we have revamped our design of the stream processor, re-architected it in this model. So now our stream processor internally will run a Samza container, which runs the user logic, and then it also spin up the job coordinator, which has a pluggable implementation of lead election, and also a pluggable module of the container process manager, which is optional and only exists for the leader. So that is a module that you can swap in to talk to different cluster management system. The container process manager, you can have the default implementation as for now is the Yarn container process manager, which is talking to Yarn RM and talking to Yarn NM to kick off all the workers. If you replace that with Mesos, then it works with the Mesos cluster. So that's that kind of concludes our solution for the second thing, which is we provide a flexible deployment model that allows users to deploy the stream processing application both in the embedded model and also in a cluster model. Last one is, okay, how do I deal with different data sources from batch and stream? What if I want to process the same logic? I'm moving an offline job. Offline job has some logics. I want to move it directly to the real time or moving it back for some validation. How do I maintain write code once and just move the data source and just deploy to different systems so that I can run on batch and run on stream? This is an illustration of that. We use the same application examples here, which is the page view event counter. Now, instead of like the input and output is a Kafka topic, now the input and output are in the HDFS system. These are showing the HDFS file path for those two different data sets, input sets and output sets. The beauty of that is we don't need to do any code change. The whole pipeline still be the same. The binary code doesn't change. All you need to do is to do a config change. The old configuration says, okay, the page view event system, stream system is from Kafka, and then the outgoing page view event per member stream is also Kafka. Now, instead of having this, instead of using this configuration, you change the configuration to point to the HDFS system and also provide the physical name of the streams in the HDFS system. Then launch the job. It will take the batch, the HDFS data files, and then now boom, you have a batch application running. So that's basically depicts the our solutions to these three big items. One is the fragmented low-level program. B is the not flexible yarn-only deployment model. Third is, okay, you can have the same application, no code change, and work in both batch and stream. And just to recap, this is our O13 architecture to enable all those solutions. So we have 4 layers layout here. At the high level, at the first layer is the high-level API, which solves the unified programming model. And then the second layer is the runners, application runners, allows us to do the local versus cluster-based launch. And then there's the deployment, different deployment models allows us to do the cluster-based deployment with Yarn or Mesos, and also allows us to do the embedded one with Zookeeper as a coordination optionally. Last one, all those is built on top of a stream processor concept, which encapsulate the different streams, local store, local states, and the remote data at the processor level. Right? So that's a conclusion of what we have to offer in the Samza 013 release. And I'm going to briefly talk about the future works. So in the future, these are the features that in our pipeline. We are actively working on a Samza runner for Apache Beam to leverage the rich syntax and the semantics expressible from the Apache Beam API. We already have a running prototype and expect to roll that out soon. And second is we're marching and progressively toward the implementation of the event time processing using our window method and improving with the persistent store for the windows for recovery, and finally we will support the event time processing. Third, we are actively working on a proposal for exact once processing in the Samza pipeline as well. And the target is for the end-to-end exact once, not just for one stage. So we are closely working together with our Kafka team members in LinkedIn to get this done. Fourth is the support for the partition expansion for the stateful applications. So historically, Samza doesn't really take the high-level Kafka consumer APIs, so it does its own partition assignments and the detection. Then when the topic partition input topic partition expands, there needs to be some manual intervention to make sure that, okay, we are capturing the new partitions in the processing. And additional difficulty here is if the Samza application is a stateful application and you have additional partitions, then all the states get shuffled. So how do you deal with that? And we are proposing some solutions to handle that case as well. Fifth is about the adjunct data sets. So we are working on a proposal to make sure that we can have an easy access to the adjunct data set. So a brief introduction to the adjunct data set. What does it mean? This is a site lookup thing. So you're processing the incoming events, and there are a lot of cases you need to do a site lookup to a data set. For example, it is either a remote database espresso in LinkedIn or some of the RESTful APIs serving a dynamic data set from the RESTful. So you want to do a declaration of the incoming event. And currently, we don't have an easy way to deal with that. There has to be some setup saying, okay, the data set, currently the solution is the data set has to be pushed through a Kafka topic, and then we bootstrap that into the key value store, then we can do the site lookup. Or if it is remote data, then the user has to write manual code to do the remote lookup. And we're going to encapsulate it into the concept of dataset, adjunct dataset, and then provide automatic way of populating the adjunct dataset and allow users, when they start the stream processing, directly accessing data. So that's the second to last. The last one, it doesn't mean it's not the least important, but this is a big task, is a SQL over streams. So this has been a long ask. We've been working gradually toward that for a long time. Even our high-level API for all those operators was originated because we want to do this SQL over stream. And one of the steps is to, okay, you need to provide the physical operators so that this SQL parsers can pass down to that layer. Luckily, with the current Fluent API, we see the lights through the tunnel. We already have a very toy version of prototype working already. Xinyu here is nodding his head because he's the one banned that out. So kudos to him. Yeah. All right. That's all for today. What I want to share, and I'm ready for questions.
You spoke about high-level APIs. Can you talk a little bit about the concurrency, level of concurrency that you're doing underneath the APIs? And also, because of that concurrency, what is the increase in throughput? Like, what are the throughput benchmarking that you have?
Okay, cool. So the high-level API is not targeted for any handling of the or changing the previous version of Samza mechanism of a parallelism. So the parallelism, even under the high-level API, it is still based on the input Kafka topic partition and the partition assignment strategy, so that you, based on this policy, you define how many tasks, parallel tasks you want to process for each of the stages. And that's pretty much my answer to that.
So throughput also is same answer, right? Like,
yes,
depends on the strategy.
Yeah.
Thanks for your presentation. I had a question about Samza support for reading HDFS. I was wondering how Samza goes about computing the splits and splitting up the work among the various task instances.
Right. So in the current implementation of HDFS consumer, Samza system, HDFS system consumer, we do provide a pluggable implementation of partition manager. So the default partition manager is basically for the set of HDFS files under the directory, one file is corresponding to one partition. But we allow user, basically the partition manager interface allows user to implement the different strategies. One of these strategies could be if you know that particular directory, the files are named based on the dates, then you can implement a partition strategy to implement the partition based on the dates, right?
I have couple of questions. First one is, let's say when you're repartitioning the data, then let's say, for example, you have 10 different jobs. Each of them are like trying to repartition on the same key. So is it possible that the system will automatically optimize on top of it? Or?
Yeah, so good question. Yeah, actually we got a lot of ask for that as well. So far, we have not really implemented any like a shared service for, for example, shared repartition service yet. But I think we'll be talking with, I want to talk with Brooklyn team regarding that, because Brooklyn has a nice layout feature for any shared service that you can provide through the streaming. So we potentially can work together with that.
Talking about one of the future thing, exactly once processing, how do you plan to implement it? Because from what I understand, it's really difficult, right?
Yes, it is not easy. I would say we already identify a lot of difficulties when we are in the design process. So the basic idea would be very similar to a watermark propagation. The I think Flink also implement that protocol. Basically, you have a token flush through the system, and then the markers using these tokens to mark, okay, this is the boundary. So again, even that model, if in your stream processing, you're reaching out to the external system to get some results, to get which is outside your control. Exact ones is possible to be done, but when you repeat that, the repeated deterministic repeated results may not be there.
One last question. So can you elaborate more on SQL over stream? I don't know much about it.
Okay, so SQL on stream is different from this high-level API because there are two different. I think for a high-level programming language point of view, there are two different scopes. One is the imperative, one is declarative. So SQL is a declarative language that allows you to just specify the data set logic, right? It's a very user-friendly, easy to use. A lot of people asking for that, but it's really hard to be applied to the dynamic data sets. The SQL standard itself is built on top of like a static data set, right? So you need some extensions in terms of the syntax, and also how do you run a SQL statement in a long-running job is also another challenge to do. Our strategy is basically we're working together with another open source project community called Calcite. They actually is providing some abstraction level to pass down the SQL syntax and the semantics into a logic algebra. And nice thing is the Calcite framework allows you to plug in and customize different physical operator implementation to this logic algebra. So that way then it allows extensions and also allows the same parser engine to be translated into different execution engine on top of different execution platforms. So this is we are working toward, right? Thanks.
Thank you very much for the talk. I especially like the bits on primitives there. It's going to make things a lot easier.
Appreciate that.
Curious about the stateful ones, though. Does that work across cluster operations as well as a single host if you're trying to carry state from one process to the other?
No. So the stateful operators is still like each instance of the state operator is still on a single host.
So it's not a global stateful operator.
Right. It is not a global. When basically the result from the state is sent to the different processing node. Right.
Thank you.
Yeah.
Does anybody have questions?
Thank you.